We have the integral of x cubed plus 1 all to the power of 3 times x squared dx. So JM was talking to you about looking at these, and quickly in your head, what do? You identify u. Okay, so what is u going to be? It's what's inside the brackets, or the square root, or the cube root, or whatever. Whatever usually has the higher power. Okay? So, what's u in this case? 3x, you mean x cubed plus 1? Sorry. There you go. So u is equal to x cubed plus 1. What is the next step?
You find du over dx?
Yes, take the derivative essentially, right? And I get 3x squared. Correct? Okay, what do you do next? Sorry? No, I just dropped my phone. I wasn't like, what did you do next? Sorry, what? What do we do? Okay, so this is where me and him differ. You can do it either way. It does not matter. I'm going to show you the way I do it, but then last class they didn't like that, so I had to do it JM's way. Okay? So all I do is I look in here, okay? I have an x squared dx. If I multiply this dx up there and divide off the 3, I get du over 3 is equal to x squared dx. Does everybody understand what I just did? Are we good?
Okay, wait, you're trying to get the constant.
The idea is to get rid of all the x's, right? So I'll do it my way and I'll do it JM's way, okay? So my way is I do this, and then I go, oh, x squared dx is equal to du over 3. I'm seeing a lot of people that don't like this method. We're going to do it JM's way, people.
I get what you're saying.
Isolate dx. It's substitution. It is substitution. But we'll just do it JM's way to be consistent. Isolate dx.
It's kind of weird that, because I always thought that du over dx or d over dx was a notation just to show that you're going to take a derivative.
No, it's like
you can actually put it.
it's like the change in u over the change in x, like delta x over delta y, right?
Oh yeah.
Okay, so we isolate dx. Does everybody understand how I isolated dx there? Okay, now sub that in for dx. It creates more work, I think. So this goes for dx, and u was that. There's u. Dx is this gong show here, so we get the integral of u to the power of 3. Our x squared still there. Du over 3x squared. That's what he does, right? And then the x squareds disappear, right? They cancel?
No way.
They do. Like that. So then we have the integral of u cubed over 3 du. Correct? This is our whole goal. We want to turn an integral that has multiple x's in it into a nice simple integral with one u. Is everybody okay with that? Okay. The 1/3 you can pull out because we don't really need that. And then we have the integral of u cubed. All right. How do you do that integral? How do you do the antiderivative of u cubed? You just do it. Okay, how do you do it? There you go. So you just add 1 to the exponent and divide by the new exponent. So I get Am I done? What do you have to do? Yeah, you got to sub back in what u was. What was u? X cubed plus 1. And I combine the 3 and the 4. Oh, when you do the antiderivative of this, you add 1 to the exponent and divide by that new exponent. That's the antiderivative. Everybody agree with that?
Yeah.
Why does it have a plus c?
Because it's an indefinite.
Because it's an indefinite integral, right? It does not have bounds here, so you have to put plus c. Are we good with that? That's the kind you were solving the last couple of days. All right. What about this one? That? Yeah. All right. So in B, what is U going to be? Exactly. So do you think you can do this one? I'll freeze it, and we'll see if we get to the same spot. U is x to the 4 plus 2. Yes. Yes, it is.
Really?
I know it looks like it, but that's the next step that we're going to talk about.
Oh, okay. I got a question, Logan.
Mm-hmm.
Is it bad if we don't move our constants out of the integral? Like,
No, you don't have to.
you don't have to. Like, you don't have to show that.
No.
Because usually I don't.
No, because you can just do it and then you multiply. Like on this one, I would have just gone from here to here.
Yeah, that's
Yeah, I'm just showing this.
So he's not that dot marks it.
I don't think so, because that's pretty straightforward. I know. Did people get to there? 1/4 u to the negative 1/2. Is that a yes?
Yeah.
And then we do the antiderivative from that, right? We add 1 and divide by the new exponent. So I'm going to get 1/4 u to the power of 1/2. Dividing by 1/2 means you're multiplying by 2. Put in u, which was x to the 4. Those will cancel. Over 2, tack on your plus c, and you're done. Does that make sense?
Oh, I just can't do that.
Any questions about that? Yeah.
Where'd you get the 2 from?
This one? So when I'm going from here to here, I add 1. So that becomes u to the 1/2. And then you're dividing by that new exponent, which flips it, the 2 up. Are there questions about this?
How do we know when to plug the original function?
Once you've done the antiderivative, so you've gotten rid of the integral sign,
Okay.
then you put the original back.
How do we know when it's simplified enough to do that? It'll be like kind of obvious.
Usually it's like a single u, or it could be like u squared plus 2u plus whatever. It'll be things that you can look at and go, oh, I just add 1 to the exponent.
Like not when it's a fraction or a root or anything like that. Like you don't want to.
Not when it's got multiple variables in it.
Yeah.
When you boil it down to a single variable, that's when you want to do it. All right. Are we good with this? This is important. This is like the basic integral. Well, actually, the basic was like when we first did what's the antiderivative of x squared, right? That's the most basic. Then the next step is this stuff. This is the next level of u substitution. But if you struggle with this, everything else is going to be complicated because you use u substitution. I know he said it's like the basic stuff, but you actually use it a lot. Even when you're doing log antiderivatives and all that kind of stuff, you use u substitution, a form of it anyway. Okay? So are we all, yeah?
So in this case, why wouldn't we add the square root into the replacement? Like right at the start, basically, when we're
Because like right here.
Yeah.
Because if you do that, if you say u is equal to, I'll write it as a power, right? If you do that, when you do the derivative, you have to use chain rule. And the problem is you're going to get this. To the negative 1/2 times 4x cubed. So you've introduced something that is more complicated, right? So it's just going to be what's inside. Okay? Any other questions? He's pointing. Oh, okay. All right. So now this is the next level stuff. Okay? Look at these two. Why? I know he was having you do this. He was having you look at this, the inside bit. What do you notice about if you do the derivative of this? You're going to get an x cubed, right? Because the exponent always drops down by 1. However, in this one, that's power of 1, that's power of 1. So it looks like it's not going to work, but we're going to do u substitution anyway. Okay? So again, u is what's inside the square root or the brackets or whatever you're doing. Okay? So u is equal to 2x minus 1. What's du? Or what's du dx? What's the derivative? Thank you, Leo. Equals 2. Isolate your dx.
Do you think Jan was fair if he just went straight for the x's, like not showing the derivative of u?
You're going to have to ask him that. Something like this is pretty straightforward, so maybe. Sub it all back in, okay? What's the problem with this integral that I've written? You have two different variables. Now, there are double and triple integrals that incorporate multiple variables. That is second year math at university. That's math 200. Okay? That's not us. We don't know how to do this. All right? So we got to get rid of that x. How do we get rid of the x? You need to write the x in terms of u. Is there an expression that relates x and u? That, right? What our substitution was. So solve for x using this. So if you move the 1 over and divide off the 2, you've now solved for x. And it's in terms of u. So that gets subbed into that x there. So I get the integral of u plus 1 over 2, x to the 1/2, du over 2. Oh, why did I write x? Sorry. Sorry, say that again?
So for all those problems we can do before, we do now with this method?
That's how you solve them, yeah. Okay, now this is gross. We got to clean this up. All right? So the 2 and the 2 can come out. right? That'll be a quarter. I can pull a quarter out. Does everybody agree with that? 2 and 2. They'll all be multiplied.
That's not a quarter.
It's in the denominator, so it's a quarter, right? Okay. So 1 quarter comes out. Now, I don't want brackets. How do I get rid of the brackets? Grade 9. Distribute it. Okay? What's u to the half times u? U to the 3 halves, because you add the exponents, right? So we're going to go, you're doing this. U to the half times u, and then the u times the 1. That's what you're doing. Add these exponents, because that's the power of 1. So I get u to the 3 halves plus u to the 1 half. Now this makes us happy because when you have an addition or subtraction sign, you can just do each one separately, right? It's nice and straightforward. So at this point, we have all u's, no x's. We have an addition or subtraction sign, so we can deal with each one separately. So what do I do to this? U to the 3 halves over 2. What does that become? What's the antiderivative of that? So it's u to the 5 over 2 divided by 5 over 2, which is the same as multiplying by 2 over 5. And then the half becomes u to the 3 halves with a 2/3 in front.
So we can basically chain rule or reverse chain rule anything now.
Not anything, but
how do we identify then what is and isn't something we can use on?
use it. My advice is always use U substitution. And if you get to the point where things aren't working, maybe you have to try a different technique. But for what the level that you're at now, U sub is your go-to technique. Unless you get into trig stuff, trig's a whole other world. Because you have to, the more complicated trig stuff, you have to start using identities to rewrite things and stuff. So. Okay, what's my final step here? Sub back in what U was. I don't even remember what it was. 2x minus 1. And you can multiply the 1 quarter in if you want. I'm just going to leave it on the outside. And I always leave stuff in fractional exponent form. But that's your choice. No mixed fractional exponents? Oh my gosh. I think that's an automatic fail. Throw on the plus C and you're done. That is the answer. This is the thing. Oh, this is why integration is more difficult, because you're coming from this, which is, that's not really a complicated function. One function times another function. It's not too bad. But its antiderivative is this. Would you have ever guessed that? No, right? What did I call it?
Integration.
He's denying.
He's pretending like he never happened.
Okay, so you sub it in. Do number 4, please. Boom. Okay, trig 1. Sine to the power of 4, 3x times cos 3x times dx, the integral of that. What is u going to be? You're close. It's not going to include the exponent. This is similar to what we were just doing, except we put trig functions in there. If I wrote this, x like that, you would sub out what's in the brackets, right? It's the same thing for trig. Go with the higher exponent. So u is going to be sine 3x. You don't include the exponent though. Okay, we take the derivative. What's the derivative of sine? Just cos. But you have to use chain rule because there's a 3x inside. So what's the derivative of 3x? 3. Off by 2. Okay. Solve for dx. So I go du is over 3 cos 3x is equal to dx. And sub it all back into the equation. U to the power of 4 cos 3x, and then dx is du. And then the cosines go away, and that makes us happy, right? So I got the integral of u to the 4 over 3 du. Is that good? Does that make us happy?
I wouldn't say happy, but
Tolerable.
yes, it leaves me satisfied.
Leaves you satisfied. I like that. All right. What's the antiderivative of u to the 4? What's the antiderivative of u to the power of 4? This. U to the 5 over 5 times 3, which is 15. Yeah, ignore the one there below it.
That's your answer.
Exactly. Trig ones can get really ugly, though, but you're not going to see those. Math 100, you'll see those. Because you use a lot of you use trig identities to break the integral up. So all that stuff plus more identities that you learned in Math 12. All right. And if you got that, I would like you to do the one right below it. Sine x over cos cubed x dx.
So if we move that up all the way, it would just be cos negative 3.
You could do that, but you don't. You will do that when you sub out the u. All right. Wow.
I feel like at this point, while we're 9, there's no sugar.
72. He's 50.
Okay, so definites.
So do we just do, did you say do u sub first and then?
Yes, so this is what we're going to talk about. Okay, so we have the integral from 0 to 1 of x times x squared plus 1 all to the power of 3. Actually, I'm going to erase the one below it because we're going to use some room. Okay. First thing is you got to just figure out the antiderivative before you do anything. So what is u going to be? X squared plus 1.
Oh, so
And then we do the derivative. What's the derivative of x squared plus 1? And then you isolate dx. So then this integral becomes x u cubed du over 2x. And you end up with this. All right? Are we good? Okay. Do not put the bounds 0 and 1 on it. Why not?
We don't want to do that yet. Use.
True. What do these represent? What does this represent? What did the 0 and the 1 represent? Between x is equal to 0 and x is equal to 1. We don't have any x's in this integral. So we're not going to put bounds on it right now. Okay? What we're going to do is evaluate it, and then we're going to bring the bounds back. Okay? So what's the antiderivative of u cubed? And 4 times 2 is 8, so I'm going to write 8, okay? Put back in your u, what is it? X plus 1? X squared plus 1. And we're evaluating that from 0 to 1. So now we can put those in because we're evaluating it from 0 to 1, correct? And they're x's. So then we evaluate it. How do we evaluate? Yeah, so the top one goes in first, right? So 1 to the 4 over 8. What am I doing? I was looking at the wrong thing. It's 1 squared plus 1 all to the 4 over 8 minus, and then you put 0 in, 0 squared plus 1 all to the 4 over 8. Yes, that is correct. That makes sense to everybody? What's 1 squared? Plus 1. 2. What's 2 to the power 4? 16. Just don't write it as 2, though. I know it is 2. Don't write it as 2 because when you do the other one, 0 squared is like nothing. 1 squared is, or 1 to the power of 4 is 1. So I get this. You've already got the common denominator. So the answer is 15 over 8. Okay. That is correct. You can do it that way if you choose. Okay? However, there's another way to do it. You have to make up your mind. All right. So at this point right here, this is an integral in terms of u. All right? Our bounds are in terms of x. Can I rewrite the bounds in terms of u?
You have to use the circadian blade
What?
The one that he said. We'd have to use a different
Oh,
blade of numbers.
okay.
Yeah.
We don't have to use a different coordinate system. So if x is 0, do I have an expression relating u and x? It's right there. So when x is 0, what does u become? 1. So when x equals 0, u is equal to 0 squared plus 1, which is 1. When x is equal to 1, what does u become? 2. So the bounds of this integral are actually 1 to 2. And you can solve that and evaluate it between 1 and 2. You'll get the same answer. Watch. So the antiderivative is u to the 4 over 8. If I evaluate that from 1 to 2, I get 2 to the power of 4 over 8 minus 1 to the power of 4 over 8. 2 to the 4 is 16 over 8 minus 1 over 8 is 15 over 8. Okay, I tend to think that method is faster because, especially when you get to bigger expressions, right, more complex integrals, we're going to do one of those in a sec. This is usually simpler than putting back in what the original was. Yeah, exactly.
So graphically, they would look the same.
Graphically, this is a rewrite. The graphs are going to look different,
But it's the same area.
but it's going to give you the same answer.
Oh.
Okay.
And the area is what we're finding.
Yeah, that's what the area under the curve is 15 over 8 between 0 and 1. So yeah, it's saying the area under the curve between 0 and 1 of this function equals 15 over 8. And the area of the curve of this function between 1 and 2 is also 15 over 8. So you've created an equivalent function in terms of the area under the curve. That's what you're doing. All right. We'll do a slightly more complex one now. Integral 1 to 5 x over root 2x minus 1 dx. All right. Just get to do the substitution and just get to the antiderivative, and I'll meet you there. And then we'll continue our journey together. So if you have a single denominator, it goes to each numerator. You break it up, okay? This is a valuable skill to remember. I guess it's not a skill. Idea. I don't know. Just remember this. I'm not sure. Dividing a single denominator goes to both. I.e., because if it's a binomial, if you have this,
Oh, yeah, just.
you cannot break that up, right? You can't write x over. I mean, you can write it like this, but that doesn't totally help you. It makes it like, then you can't go like that. Like, it doesn't really help, right? When it's a binomial, you have to. This leads into long division and stuff. You're not going to see that in this course, right? But a single denominator like this, or monomial, I guess, you go to each one. Then you subtract the exponents. So u over u to the half is u to the half. And the other one I'm going to flip up to make it negative u to the half. Now we can integrate or find the antiderivative. What's the antiderivative of u to the half? Is that okay? The note, like, doing integrals it gets kind of messy. Does everybody understand what I just wrote here?
Well, yeah, how come the integral goes from like a squiggly line to a straight?
Because that's the anti. So this is saying the integral of this function. You find the antiderivative, so that goes away. This is evaluate this between 1 and 9.
Oh, okay.
Okay. So which one goes in first? You want to cancel the 1/2 with the 2's? Okay. Is that easier? So I got this. That? You like that? Is that better? Okay. 9 goes in first, right? Okay. Minus. When you subtract, please, for the love of whatever, bracket what you're subtracting. Because you will get it wrong if you do not. Okay, so I just plugged in the 9 and I plugged in the 1. I'm subtracting all the 1s, so it's all in brackets. Okay? What does this little 2 represent as an exponent when it's in the denominator? Square root. What's the square root of 9? 3. What's 3 to the power of 3? So we get 27 over 3. I'm going to leave it as 27 over 3. I know that is a number, a whole number, but I'm going to leave it as 27 over 3. 9 to the power of a half is minus. The 1s are nice because they're just 1s, right? 1 to 3/2 is just 1. And 1 square root is just 1. But there's a minus out there, so it's minus 1. And this is why I left it as a 1/3, or 27 over 3. Because I have 27 over 3 minus a 1/3, which is 26 over 3. 3 minus 1 is?
Wait, hold on.
Oh, yeah. 3 minus 1 is not negative 2. And because we're in calculus, we can do the actual answer.
That seems like a pretty nice extraction.
32 over 3. Oh my gosh.
10 and 2/3.
Oh, you hurt my soul. You hurt JM's soul too. You're hurting everybody's souls. There's your questions, people. 55, 57, 59, 65. I strongly implore you